Hello, we're back talking about exponential applications. And this time I wanted to talk about growth and decay, that is exponential growth and decay, in terms of a fixed rate of growth or a fixed rate of decay. And I'm going to define this rate as being between 0 and 1, that is to say between 0 and 100%. Those are really saying the same thing. So let's consider some example of a constant rate of growth. Let's say maybe a bank account or something like that. Suppose we had, for example, a constant rate of growth of 5%. So you invest some money, you leave it in there for a year, and then it gains this 5%. You leave the original investment plus the 5%, and you reinvest that the next year, and it gains another 5%, and so on and so forth. Let's see how this would look graphically by applying this 5% to this growth formula. So let me make a little table, a little XY table here. Okay. And this growth rate, when I use it in the formula, I'm going to have to go ahead and turn that into a decimal valued number. So 5% is 0.05. That's what I'm going to use. And my equation then is going to look like y equals a, whatever amount I start with. Let's make up an amount that we start with. Let's say $100. We put $100 in there. There's my a, times 1 plus my constant rate of growth. If we're calling it 5%, then I can add those two together and put 1.05 in here to the x. Okay. When x is 0, then we're talking about our initial investment, and this equation would give us back our initial investment, what we called $100. Remember, anything to the 0 power is 1 times 100 is 100. So there's our initial investment. Now let's stick in some other values. Let's go with 5. What if I put a 5th power in for x? And I'm going to cheat here and use my fancy calculator. Okay, if I put in 5 for x, I'm going to round it to the nearest dollar because I don't really have a fancy scale here that's giving us cents and everything, but it's about $128 in this financial example. Let's take a look at 10 years and maybe 15 years, 20 years, that might be enough. At 10 years, then I put an exponent of 10 in here, and I would be looking at about $163. Okay, after 15 years, this would give me about $208. After 20 years, I'd have about $265. Started with $100, and after 20 years, I have $265. Okay, that's not that great, but you could probably do a bake sale or something. But let's see what this looks like on the graph to model this growth. So if I start with 0, 100, you can see that I adjusted my y scale here so that I have increments of 100. And my x scale, which in this example I'm calling years, goes in increments of 5. 5, 10, 15, 20, 25, 30, so on, up until 50. I probably didn't need that far, but that's okay. Let me just put in my values here. 0, 100. That looks like that right there. 5, 128. So here's 5. 128 is, I don't know, I'm taking a pretty good estimate there, but not precise. How about 10 years? 163. So it's still not raising very fast, as you can see here. 15 years, 208. So here's my 15. I'm a little bit above 200, but just barely. 20 years, 265, so I'm a little bit about here. Let's go ahead and put in a few more values. I'm actually interested what this looks like if we continue. And you can continue the table on your own. I'm just going to stick in a few more values that correspond to these guys. How about, let's go to 30 years. Okay. So we put in 30 years, I get about 432. So 30 years, 432 is kind of like, about there. How about 40 years? Gives me 704, roughly. Okay, 40 years, 704. Interesting. All right. How about 50 years? Well, after 50 years, we get 1146. Oh, that's interesting. that would put me above my scale probably about there. So if you connect the dots, notice how your investment is growing, even though it's just a fixed rate, okay? But you keep reinvesting it. This is what happens over time. It starts off kind of slow as it grows, but then, wow, it really starts to pick up speed over time. Okay? And this is kind of what happens with exponential growth, which is why it's so cool if you can apply it to an investment, and why it's so terrible if you're paying out an exponential issue with like a credit card or something like that. I'm not sure if they all work that way. You can always check the back of the credit card statement and see exactly how they calculate it. Now suppose we did something a little different, okay? Suppose we doubled our initial investment. How much would that change what we have? Well, that's okay to look at, and I think we've done that in a different example. We'll go ahead and do that on your own, but let's instead double our rate and see what happens there. So let's consider, what if our rate, instead of 5%, was 10%, which of course is 0.1 as a decimal valued number. And I do another table like this, where I've got some x value, my y value, and let's just go by tens on this one. 0, 10, 20, 30, 40, and 50 years. It's probably getting to be off the screen a little bit. Looks like we got a little bit more space. Okay, we're going to keep the same initial investment of $100. And we're going to demand 10% instead of 5%. And somebody in the world gave it to us, so here's the equation. Add 10% to 1, that gives you 1.1 to the x. Let's see what that looks like. Okay. There we go. So at 0, again, anything to the 0 power is 1, so we have our initial investment. That would, of course, start the same on the graph. After 10 years, it looks like we've got 259 about. Okay, I'm just going to write all the values and then plot it. After 20 years, looks like we've got, 673. Wow, okay. After 30 years, 1745. After 40 years, 4,526 about. And after 50 years, we got about 11,739. 11,739. And obviously, we're way off the scale here, so I should have gone with the shorter timeline there. But at 0, we're 100, okay, same spot. At 10 years, we're already 259. Ooh, about there. Let's consider 15 years. I didn't write it on the table, but that gives us about 418. So maybe about there. And then 20 years, 673, about there. Okay. 30 years, 1745, that's way off my scale. How about 25 years? Let's see what we got there. That's 1083. So I'm about here after 25 years. And you can see that we have the same pattern here. But because we changed the rate, that thing's rising much quicker. Okay? It still starts off, quote, slow, and rises faster and faster as you increase the time. But wow, that was a big difference, a big deal. So if you want to make a big difference in your financial life, just increase that rate. Now, I also wanted to consider one example of a decay with a fixed rate. Suppose we had some kind of atomic decay, and I've discussed examples like that previously. Suppose we had some kind of atomic decay, and your professor comes and says, hey, we're losing 15%. We're losing 15% of this atom per period, whatever period that is. Let's take a look. X is going to be our number of periods. Maybe it's every 5 minutes you lose 15%. Maybe it's every 5,000 years you lose 15%. Different atoms that decay decay at different rates. But let's just call it generically periods. And then you can insert whatever number of units you want there, if you want it to be years or minutes, whatever you want. So if I'm considering a decay of an atom, here's my little XY table corresponding with a rate of decay of 15%, which is 0.15, then my equation for y becomes whatever amount we started off with. Let's start up here at 1,000. 1,000 whatever. Let's say we had 1,000 grams times, if I plug in this rate of 15% into this decay equation, 1 minus 0.15, I would get 0.85. And this is to the x power. Notice that this number in here is less than 1. It's between 0 and 1. It's a fraction represented as a decimal. But this fits our previous definition of decay when x is positive and has positive values. So let's take some positive values. At 0 time, of course, we know what we get. It's what we started with, 1,000. And then let's do some, how about 10 years, 20 years, 30 years, 40 years, and that might be enough. After 10 years, I'm going to put a 10 in there. And I already have this in my fancy calculator. I'm totally cheating. So let's see, 10 years. It looks like we're down quite a bit. Let me do 5 years. 5 years, we're down to about 444. Since I didn't write it down, I'll go up to 10. 10 years is about 197. Wow, that's crazy. From 1,000 to 197. 20 years, or 20 months, or 20 minutes, or 20 whatever unit you have. That takes us down to about 39. Wow. After 30, we're down to 7.6. How about 40? Down to 1.5. Wow. And you're going to start to see that flatten out and not decrease much faster after that. But you can see that the initial decrease is pretty dramatic. So let me put some of these values up here. We're starting with this amount of whatever, let's say grams, and then I'm going to put in 5. After, let's say 5 minutes, it's more fun. After 5 minutes, we get down to 444. Okay, so that's 440, I don't know, about right there. 4. After 10, we're down to 197. That's pretty close to 200, maybe about right there. After, how about 15? We don't have a 15 there. We're at 87. Okay, so about here maybe? After 20, down to 39. Wow, that's getting low fast. 37.6. On my scale, that's hardly noticeable. So what you'll notice is that it starts going like this. Rapid loss and then sort of flattens out like that. And if we use strictly this model, it actually never reaches 0, but it gets very close. At infinity, you can say it's down to 0, infinite time. But so there are a few more examples that I hope you enjoyed, where we have a constant rate and we know what that rate is, and we can plug that into a formula for exponential growth or decay.